Welcome to This Explainer. Today, we are jumping right into the guts of your home to break down exactly how modern heating and cooling systems actually work. If you're a homeowner, or honestly just someone who loves geeking out on the hidden machinery keeping everyday life running smoothly, you already know that keeping a house perfectly comfortable year-round is a massive expense. So we're going to demystify the tech behind it all, giving you the real, actionable knowledge to make the most energy-efficient and cost-effective choices for your own setup.
All right, let's kick things off by busting a massive myth right out of the gate. You know that refreshing blast of air you feel on a sweltering summer day? You'd naturally think your AC is in there generating cold air, kind of like how a furnace generates heat. But nope, it doesn't create cold air at all. It literally just removes heat. Think of it like a giant thermal sponge. It soaks up all the heat and humidity inside your house and then just wrings it out outdoors.
To keep this explainer moving and highly practical, we're following 5 clear sections today. Section 1, the refrigeration cycle explained. Section 2, enter the heat pump. Section 3, heat pump versus furnace. Section 4, air source versus geothermal. And finally, Section 5, choosing your ideal system.
Section 1, the refrigeration cycle explained. Moving heat, not making cold.
Okay, so to really get this, we got to go all the way back to the foundational physics pioneered by Willis Carrier in 1902. The absolute most crucial point here is that cooling is simply a continuous cycle of moving thermal energy from the inside of your house to the outside. And it pulls off this magic trick using a highly specialized chemical called refrigerant. You can think of refrigerant as the lifeblood of the entire system. It constantly flows through copper tubing, shifting back and forth between a liquid and a gas state, specifically to absorb and then dump heat.
Let's actually walk through this brilliant 4-step journey. First up, you have the compressor. It acts like a giant pump, squeezing the refrigerant gas under high pressure and sending it out to the condenser coil outside. That's where it releases its heat into the outdoor air and condenses back into a liquid. Make sense? Then it flows back inside through an expansion valve, which drastically drops its pressure and temperature. And finally, this freezing cold liquid hits the evaporator coil inside your house. Warm indoor air blows across it, the refrigerant absorbs that heat, turns back into a gas, and boom, fresh, newly chilled air is pushed right back into your living room. The system just repeats that loop until your thermostat is happy.
Section 2, enter the heat pump, the refrigeration cycle in reverse.
Now take that exact same cooling logic we just went over, but apply it to heating your home. That's essentially what a heat pump is. It's an air conditioner that has the ability to run backward. To really grasp why heat pumps are completely changing the game, we have to look at a metric called COP, or coefficient of performance. It's just a simple ratio measuring how many units of heat you get for every single unit of electricity you pay for. A standard electric resistance heater, it has a COP of 1. You put 1 unit of electricity in, you get 1 unit of heat out. But heat pumps usually operate with a COP somewhere between 2 and 5.
Get this, because heat pumps are just moving heat around rather than creating it from scratch, they can achieve a jaw-dropping 300 to 600% efficiency. By extracting ambient heat from the outside air, yes, even when it feels totally freezing to us, and pumping it indoors, they effectively break what we always thought were the hard and fast rules of energy consumption. You are literally pulling free heat energy right out of the environment. It's like nature's ultimate discount code, and you're only paying for the electricity it takes to run the pump and the fans.
Section 3, heat pump versus furnace, the ultimate heating matchup.
Let's pit the heat pump against the classic basement heavyweight, the traditional furnace. Unlike the heat pump and its crazy multiplying power, we measure a furnace using an AFUE rating. This basically tells us how efficiently a furnace converts its actual fuel source, stuff like natural gas or propane, into raw heat. Now, a super high-efficiency furnace can hit an AFUE of 97%, meaning almost no energy is wasted as exhaust. But here's the catch. Mathematically, it can never exceed 100%. It's literally impossible to get more energy out of a fuel source than what naturally exists inside of it. So we're looking at 2 totally different approaches to comfort here. On one hand, a heat pump uses a little electricity to borrow heat from outside in a really slow, steady, and hyper-efficient cycle. On the other hand, a furnace just brute forces the job. It's almost like having a controlled, fire-breathing dragon down in your basement. It burns fossil fuels to aggressively blast hot air straight into your ductwork. Because of this, furnaces supply air at much higher discharge temperatures. Heat pumps, alternatively, give you longer, gentler heating cycles that keep your indoor temperature incredibly consistent, though, yeah, they can struggle a little bit when the outdoor temperature drops into the extreme negatives.
But hey, if you live somewhere with brutal, freezing winters, there's absolutely no need to panic and pick just one. You can actually install a dual fuel system.
This hybrid setup runs the ultra-efficient electric heat pump during the milder fall and spring weather. Then, when the dead of winter hits and freezing temperatures demanded, the system automatically tags in the gas furnace for that reliable high heat output. It is truly the best of both worlds, keeping both your carbon footprint and your utility bills as low as possible.
Section 4. Air source versus geothermal. Where are you pulling heat from?
All right, so if you do decide to go to heat pump route, you've basically got two radically different ways to grab that outdoor thermal energy. Both systems perform the exact same job, but they pull from totally different sources. Air source models grab heat right out of the ambient air above ground. They look pretty much exactly like a standard AC unit sitting next to your house. Geothermal models, which are also called ground source heat pumps, tap into the thermal energy buried deep beneath your lawn using a series of underground loops. Because of that, geothermal requires some serious yard space to dig either horizontal trenches or deep vertical wells. So why are geothermal systems the undisputed kings of efficiency? Well, it is all about temperature stability. No matter how absolutely freezing the winter air gets above ground or how scorching the summer sun is, the soil beneath the frost line just hangs out at a cozy, constant 50 degrees Fahrenheit. For a heat pump trying to extract heat in the middle of January, pulling it from 50-degree soil provides a massive mechanical advantage compared to trying to scrape it out of 0-degree air.
When we look at the hard numbers, there's a pretty clear trade-off going on. An air source heat pump is highly accessible, costing roughly between $4,500 and $25,000 to install. Geothermal? That requires a much higher upfront investment, often $8,000 to $30,000 or more simply because of all the excavation work required. However, geothermal pays you back with extreme longevity. The heat pump unit itself is good for 20 to 25 years, and that super expensive underground coil you buried, that thing can last for 50 years, all while deeply slashing your monthly energy bills by 25 to 50% compared to an air source model.
Section 5. Choosing your ideal system, making the upgrade.
We've covered the mechanics and the matchups. Now, how do you actually apply all this to your own house? Choosing the right system isn't about finding some singular, magical best machine. It's about objectively evaluating your unique situation. Think about your local climate. Are we talking mild winters or polar vortexes? What's the state of your home's insulation? And do you even have existing ductwork, or will you need to look into a ductless mini-split system? You also have to weigh your budget for that upfront installation against your desire for long-term operational savings and, practically speaking, whether you even have the outdoor space for something like a giant geothermal trench.
Now, I know those upfront costs can sound a little intimidating, but fortunately, both heat pump setups qualify for some really generous federal tax credits right now. If you go with an air source heat pump, the energy-efficient home improvement credit lets you claim up to $2,000. For geothermal, the residential clean energy credit gives you a straight 30% credit on the cost of the system. And get this, there is no dollar limit. But timing is absolutely critical here. Both of these federal tax credits expire at the exact end of 2025. And hey, if the upfront capital is still a hurdle, the industry is totally shifting. There are now HVAC leasing options popping up that bundle the equipment, the installation, and the ongoing maintenance into one single, predictable, flat monthly fee.
So I'm going to leave you with this final thought. For decades, we have relied on simply burning fuel to stay warm, but the rules of the game have completely changed. Next time you look at your utility bill, ask yourself, are you going to keep paying to make heat, or are you finally ready to just start moving it? Taking the time to understand this tech is the very first step toward turning your house into a model of sustainable comfort. Thanks for joining me on this explainer, and I really hope this helps you make the perfect climate choice for your home.